Right, so this evening we're just going to answer the 5 problems on eigenvalues. Right, again, this is a rather an advanced exercise or advanced matrix operation. Right, so eigenvalues, just to give you a brief background. I mean, you already have this in your slides. Eigenvalues are used to determine the shape, basically, of a multivariable function, right, which will be very useful later on in our module on optimization. Right? This is fairly useful to determine the shape, whether the function is concave or convex. Right? Uh, it's essential in determining the definiteness of a given matrix. Eigenvalues are also useful in eigendecomposition, which basically simplifies a matrix into simpler components, which is practical and essentially useful in econometrics and in dynamic indifference equations, which is part of macroeconomics. Or I'm not sure if you're gonna take that up in your macro later on, but just to be sure, just to make you a little bit comfortable with eigen decomposition, right? So I'll be including this as part of the module, right? So let's answer these 5 questions. I'm pretty sure some of you had some difficulties in some of the items here, but let me assure you that some of the most of the items here are fairly straightforward. So let's start off with the first question, which asks us to determine the values of lambda that sets the determinant of this matrix equal to 0. Now, at first glance, you would notice that the lambdas are essentially the eigenvalues of the of this particular matrix. Now, to get the value of lambda that sets this matrix or sets the determinant of this matrix equal to 0, we'll just have to find the determinant of the left-hand side. Set equal to 0 and find the values or the roots, the lambda, values of lambda that will make that determinant equal to 0. So let me share the screen. Let me share my PowerPoint screen. Okay. So let's copy that matrix. So that matrix is, we're just basically getting the, or maybe you can just get the determinants right away. No? So to get the determinant of the matrix, right? Oh, sige, let's just impute the matrix here so that everyone can see later on when you replay this. Right. So the matrix is 1 minus lambda. Okay. This is 0. This is 0. Okay. This is 0. This is 2 minus lambda. This is square root of 2. Okay. This is 0. This is square root of 2. Oops, this is square root of 2. And this is 3 minus lambda. So notice here, if you try to uh, observe the steps, or to trace back the steps, how how this matrix was constructed, you just basically subtracted lambda that is multiplied by an identity matrix. So basically, we wanted to get the eigenvalues of this given matrix. Now to do that, let's try to solve for the determinant of this matrix, and let's use the first row. Right, pretty straightforward. Let's use the first row. So the first row, the determinant, or using the first row, the determinant of this matrix. Let's name this as A, or well, let's name this as A minus lambda I. Okay. Appropriate name for this matrix because we're basically subtracting matrix A with lambda times an identity matrix. So this is equal to 1 minus lambda times, right? So since this is located in the first row, the index, this is located in the first row, first column. The index of this element is 1, 1. The sum of those indices is equal to 2, so it's an even number. Hence, you still get a positive element right here, right? And then you delete the first row in the first column, just like how we do it in a 3 by 3 matrix. You delete the first row in the first column and get the determinant of the remaining submatrix. So that will be the determinant of, I'm doing this step by step. So that's 2 minus lambda. This is square root of 2 This is square root. This is again square root of 2. And this is 3 minus lambda. Okay. So obviously, we're looking at this expression. This is equal to 1 minus lambda times 2 minus lambda times 3 minus lambda minus square root of, or minus the product of the, or minus the square of the square root of 2, and that's just essentially minus 2. Right? Earlier, I got a message asking me if we can factor this out, or if this is actually factorable. Now, it takes a bit of strategy. No? It takes a bit of strategy. So, looking at this expression, right, some people would just evaluate this as it is, but of course, that's going to be difficult. But one way to solve this is to, well, let's evaluate, set this equal to 0, okay? Because this is already the determinant, right? That's already the determinant of basically a minus lambda I. So that's 1 minus lambda times this bracketed term. And obviously, you already have one of the eigenvalues, right? Because this is a product. This is a product of these two terms, and therefore, if the product of these two terms is 0, then this first binomial must be equal to 0, right? So you already have one of the eigenvalues. So from this equation, you already know that 1 minus lambda is 0, and your first eigenvalue would be equal to 1. Okay. Now, how about the second factor? The second factor is we're just basically dissecting this 2. So this is 2 minus lambda, 3 minus lambda minus 2 equals 0. Now, we can solve this, right? We can solve this, and we'll be getting a quadratic expression. So that's going to be 6, right? So 2 times 3, 6, minus 5 lambda, right? Because you have negative 2 minus negative 3, you have negative 5 lambda, and then you have lambda squared, right? Minus 2 equals 0, right? Now, you subtract 2 from 6, and you'll have a really neat quadratic expression, which is equal to lambda squared minus 5 lambda plus 4, right, equals 0. And therefore, if I factor these two together, if I factor these two, I'll end up with what? I'll end up with lambda minus 4 and lambda minus 1, right, equals 0. Okay? Diba? When you multiply this, you have lambda squared, you have negative 4 lambda minus lambda, you get negative 5 lambda. 4 times 1, negative 4 times negative 1, you have positive 4. That's equal to 0. And therefore, your three eigenvalues are actually 2. You have two eigenvalues, right? You have two eigenvalues. So therefore, if you factor this out, this is essentially equal to 1 minus lambda, 1 lambda minus 4, right? Lambda minus 4 and lambda minus 1 equals 0. Okay. So essentially, if I equate this lambda minus 4 to 0, and if I equate this lambda minus 4 to 0, so my other eigenvalue would be lambda equals 4. And you can test that out. You can test that. So let's try, say, substituting 1 let's try substituting 1 in lambda. Right, so let me just copy this matrix. Okay. If I substitute 1, which is our, well, let's say candidate eigenvalue, if I substitute 1 in lambda, this becomes 1 minus 1, and this becomes 0. This becomes 2 minus 1, this becomes 1, and 3 minus 1, this becomes 2. And having a row of zeros implies that the determinant, right, or automatically the determinant of this matrix will be 0. Okay. Now, what if we use 4? Let's try to use 4. So that's going to be 1 minus 4, that's negative 3, right? The next matrix would be 2 minus 4, negative 2. And you have 3 minus 4, you have negative 1. Okay? So let's try to solve for the determinant. So the determinant of this matrix, right? So the determinant of this matrix would be negative 3, right? So negative 3 times what? The determinant of this 2 by 2 matrix. So that's going to be 2 minus 2. And this will just be equal to 0 because this bracketed term is now will be equal to 0. Okay. So yeah, it's factorable, right? It just needs a quick manipulation, so to speak, right? And it's actually easier than factoring a polynomial of order 3. So that's basically number 1. So lambda is equal to 1 and equal to 4, and that turns the matrix into that turns the matrix A into a singular matrix, or that ensures that the determinant of the said matrix is equal to 0. Right? So essentially, the eigenvalues would be equal to 1 and 4. Right? Well, again, for those who just came in, this session is recorded, so you can just refer back to this video later. And if you have questions, you can post that in our topic Q&A, right, for your reference. Okay, so that's number 1. Now for number 2, let's try to solve for the eigenvalues of this matrix. Right? So the matrix is again a 3 by 3. It's a 3 by 3 matrix of real numbers, or actually integers. 1, 1, 1, 0, 2, 2, 0, 0, 3. Now, actually, there's a theorem, right? There's a theorem that you can actually find this in Dano's textbook, or probably in other textbooks in mathematical economics, that the product of the diagonal, right, the product of the diagonal is essentially the eigenvalue, or actually the diagonals would be the eigenvalues of this matrix. Okay. We can verify that, right, by solving for this matrices eigenvalues. Right? So yeah, the diagonal elements are basically the eigenvalues for this triangular matrix. So essentially the eigenvalues would be 1, 2, and 3. But let's verify. So let's subtract. Let's suppose this is let's consider this as matrix A, and let's subtract the diagonal with say alpha, right? And get the determinant. Set it equal to 0, and then solve for alpha. So let's set this as 1 minus alpha, right? This is 2 minus alpha, and 3 minus alpha, right? And get the determinant. So the determinant of this matrix must be equal to 0, and then we solve for alpha. Okay. So we can use for convenience, we can just use third. We can just use this third row. Okay. So that's going to be 3 That's going to be 3 minus alpha, okay, times the determinant, right, times the determinant of the matrix obtained by deleting the third row and the third column. So that's essentially 1 minus alpha, 1 minus alpha, and 2 minus alpha, right? So the determinant, the determinant of a minus alpha I is equal to this expression, and setting this equal to 0. And that's pretty straightforward, no? So since all of them, since this product is equal to 0, then obviously each of them will be equal to 0. Right? That's the nice thing about triangular matrices, no? You can get the determinant easily by multiplying, basically by multiplying the diagonal or getting the product of the diagonal terms, and the eigenvalues of a triangular matrix are essentially its diagonal elements. Okay. Hi, good evening. So for those who just came in, we'll be recording this session, and for your reference, you can just rewind, or you can just play and pause this video later on. And again, if you have questions, you can just post it in our topic Q&A, right, for your reference, or maybe you can address that later. Now, going back to this example, you have a triangular matrix whose lower triangular elements are 0, right? So that's a really convenient matrix, because for a triangular matrix, for an upper triangular matrix like this one, the diagonal elements will be its eigenvalues. And true enough, when we try to solve for the eigenvalues of this matrix, we get this expression, right? Now, since this is a product, so all of the factors, or when the product of these factors are equal to 0, then each individual factor will be equal to 0, or possibly equal to 0. So therefore, alpha 1 would be equal to 3. The next eigenvalue would be, the next eigenvalue would be equal to 1. And the next eigenvalue would be, actually, if you were more comfortable, you can just say that alpha 1 is equal to this first element, right? Alpha 2 will be equal to the second element, or the centermost element in this matrix, and alpha 3, sorry, alpha 3 be equal to 3. So number 2 is pretty straightforward, so long as you know the properties. So two things, right, involving triangular matrices, triangular and diagonal matrices. The determinant of a triangular matrix will be the product of its diagonals. And the eigenvalues of a triangular matrix will be the diagonal elements. All right, so that's number 2. Okay. Any questions? Any questions so far?
Is this applicable to lower diagonal
Yeah, that's also applicable for lower diagonal. Or let me verify. I'm pretty sure that's also applicable to uh, lower triangular matrices. Yeah, so it doesn't really specify what kind of triangular matrix. So it could be either upper or lower triangular matrix, right? So all the diagonal elements will be its eigenvalues. So let's proceed to number 3. Right? So number 3, we're just asked to verify, to show that if that alpha 0 is an eigenvalue of A if and only if A is singular. All right. So recall that when we try to solve for eigenvalues, we're looking at this linear expression, right? So a little proving exercise, no? Uh, and we know that alpha here would be the eigenvalues, right? Or, well, alpha here is the scalar or the eigenvalue that is associated with the eigenvector x, all right? Now, if alpha is 0, then we have ax equals 0. That's correct, right? Since, well, if alpha is 0, then the right hand term would be equal to 0, right? Or the vector, when you multiply that with the vector, it would be equal to 0. Okay. Now, since the eigenvector is set to be non-equal to 0, since eigenvector is non-zero, okay, so it means that in this homogeneous, basically in this homogeneous equation, we have a non-trivial solution, i.e., this homogeneous system has non-trivial solution. It implies that the determinant of A is 0. Okay? And therefore A is singular. Okay? Kahit baligtarin mo yan, the fact that that the right hand side is 0, or the fact that A is singular, it means that it doesn't have an inverse, right? The fact that it doesn't have an inverse, and the only way for that to happen is if alpha is 0, all right? So even if we start with the fact that A is singular, right? So sige, para for the sake of completing the proof, right? We have AX equals alpha X, right? So if A is singular, then the determinant of A is 0. Basically, I'm constructing the other side of the proof, no? Determinant of A is 0. This means that for this system of equation, right, if the determinant is 0, and X is non-zero, okay? If the determinant of A is 0 and X is non-zero, the only plausible thing, right, is that the only possibility, right, the only sensible possibility is that alpha X must be 0. But since X is supposed to be non-zero, then alpha, or the eigenvalue, must be 0. So binaligtad lang natin. In the first part, I assumed first that, or I set first the eigenvalues to 0, and this gives us a uh, straightforward proof, no, that if alpha is 0, then of course this will be a homogeneous system. It becomes a homogeneous system, and since the eigenvector is assumed to be non-zero, right, or it's supposed to be non-zero, then alpha, or sorry, A, the determinant of A must be 0. Okay. Similarly, right, if A is singular, then the determinant of A must be 0. So if the determinant is 0, if the determinant of A is 0 and X is non-zero, the right-hand side must be equal to 0. But the only way for the right-hand side to be equal to 0 is if alpha is 0. And therefore, that completes the proof for number 3. Okay. Of course, you're not gonna have that in the exam. This is just an exercise. Because the thing is, if you're not yet comfortable if you're not yet that comfortable answering mechanical questions like 1 and 2, then how you're supposed to be comfortable, say, answering proofs like this? So it takes a couple of practice sessions, right? Or you'll have to really have to practice answering problems like this. Okay. All right. So let's move to number 4. So a real symmetric matrix is, again, you may want to take note of this regarding definiteness of a matrix. This becomes essential in optimization when you wanted to verify whether our candidate solution is a maximum or a minimum, local maximum or local minimum. That's going to be essential later on for multivariable optimization. Okay. So as I said, a real symmetric matrix is supposed to be positive or negative definite if all of its eigenvalues are positive or negative, if it's a negative definite matrix. A real symmetric matrix is said to be positive semi-definite if the eigenvalues are positive and at least one vanishes. So yung isa magiging equal to zero. It becomes indefinite if it has positive and negative eigenvalues. Suppose that A is equal to this matrix. Then let's examine A for definiteness. Actually, you don't have to solve anything in number 4. You don't have to solve anything in number 4 na. Kasi, well, obviously this is already a special case of a triangular matrix, right? It's a diagonal matrix. Okay? So since this is a diagonal matrix, of course, if you want, you can still verify this. But since this is a diagonal matrix, the elements of the elements or the diagonal elements will be this matrices eigenvalues, right? So the eigenvalues of this matrix A would be 3, -1, and 2, right? So based on our criteria, you have a positive number, which is 3, you have a negative number, which is -1, and you have a positive number, which is 2. So there's a positive and a negative eigenvalue. So therefore, matrix A is an indefinite matrix. Right? And just to give you a context, if a matrix is indefinite, right? If a matrix is indefinite, this is the multivariable equivalent of a function a that has an inflection point, right? Or a point where it's neither a maximum nor a minimum. Or in a multivariable calculus, this is equivalent to having a function that has a saddle point, right? It's neither, again, the point corresponding to this matrix will neither is neither a maximum, nor a minimum. Okay. So 3 and 4 doesn't really require, actually 2 and 4 doesn't really require a lot of computations because you just have to examine and just identify what kind of matrix A is. Okay. And number 5, finally, number 5, let's try to mechanically find the eigenvalues of this matrix. Again, this seems to look like an indefinite matrix. Okay. Sorry, for those who are still looking at the video, it's displaying the PowerPoint presentation. So let me just go through a new slide. Right? Just reiterate, no? Okay, so we have a 3 by 3 matrix. Okay, so you have 3, 3, 0, 0. You have 0, -1, 0, and 0, 0, 2. This is for number 4. Now, again, this is a triangular matrix, and obviously, and since this is a triangular matrix, the elements along the diagonal would be this matrix's eigenvalue. So, well, let's denote alpha as the eigenvalue. So, alpha 1 would be 3, alpha 2 be -1, and then alpha 3 would be 2. Right? So, you have both positive and negative values. Therefore, A is indefinite. right? So whatever candidates in multivariable calculus or multivariable optimization, as we will discuss later on, any candidate solution that is associated with this indefinite matrix, right, will be a saddle. It's basically a saddle point. Right? It's going to be a saddle point. Okay. So again, let me just reiterate for the newcomers. I'll be recording the session. So it's actually recording now. So if you have any questions, you can just replay this video later, right? And if you have questions, you can just post it later in our topic Q&A. So numbers 2 and 4 doesn't really require any mechanical solution so long as you know the properties of the matrix. So let's move on to number 5. So okay, number 5, the matrix is equal to, or matrix, let's denote that as matrix A. So you have 0, 0, -2, you have 0, 7, 0, and 1, 0, -3. Okay. Let's use that as our matrix. Okay. Okay. So let's solve now for the eigenvalues. Right. So let's subtract. Well, let's subtract the diagonal. So don't be mistaken. This is not a diagonal. This is not a triangular matrix. No, this is not a triangular matrix. Well, this has the diagonal. Well, the off diagonal elements are not all equal to 0. Right. So you'll have to be very careful. Right. So let's transform this, and let's, instead of using lambda alpha, let's try to use lambda. Right. So this becomes negative lambda 0, -2. This becomes 0, 7 minus lambda 0, 1, 0, -3 minus. And let's try to get the determinant. Maybe you can use let's try to use the second row, no, two zeros involved, right? So that's going to be 2, 2, 2, 1, 2, 2. So that's going to be 7 minus lambda times the determinant of the matrix obtained by deleting the second row and the second column. So that's practically negative lambda times -3 minus lambda, okay, plus 2 equals 0. So in this particular form, you already have an idea of what lambda is. So you have two factors here, right? This is a product of 7 minus lambda quantity or binomial times this term. So essentially, our first eigenvalue is already solved. So our lambda 1 would be equal to 7, right? Since 7 minus lambda is 0, and therefore lambda would be equal to 7. Right. For the second set of eigenvalues, we'll have negative lambda, -3 minus lambda plus 2 equals 0. Right? And just redistributing terms, right? You have 3 lambda. You have 3 lambda plus lambda squared plus 2 equals 0. So this becomes equal to what? Lambda squared. So let me rearrange the term. So this becomes lambda squared plus 3 lambda, right? Lambda squared plus 3 lambda plus 2 equals 0. And I can easily factor this out. So this is basically equal to right? I do hope that at this stage of the course, or at this stage of the program, you're already sort of comfortable factoring out quadratic equations, right? So kumbaga at the first glance, you'll be able to factor out quadratic equations because that's gonna help you, right? So in this case, you have lambda squared plus 3 lambda plus 2, and therefore, if I factor this out, this is equal to lambda plus 1, and you'll have lambda plus 2 that equals 0. And therefore, my other set of eigenvalues will be lambda 2 equals negative 1, and lambda 3 will be negative 2. So three eigenvalues. You have 7, negative 1, and negative 2. Okay? So that basically solves that solves all of our problems in the exercise set. Are there any questions at this point before we move on to eigendecomposition? Basically, I'm just going to discuss whatever it is in the slides, no? And just to give you some context as to why we are doing eigendecomposition. Any questions or clarifications?
None
And so far,
sir.
Okay. Okay, just check the chat. Okay. So again, if later on you find something that's a little bit too confusing, you can just post it in the topic Q&A. And of course, as practice, maybe you can start answering the problem sets already. One of your classmates have finished the problem set already, right? That's actually advantageous for that person because he has more time. He's gonna have or he or she's gonna have more time answering the other problem sets. So let's try to move on to eigendecomposition. All right. Let me just share the slides for that. So basically, eigendecomposition tries to, or is one of the techniques in matrix algebra that sort of decomposes the matrix into simpler components. And by simple, we mean eigenvalues and eigenvectors. So suppose you have a symmetric matrix A, all right? And again, this is only applicable for symmetric matrices or square matrices to be exact. No, uh, if you have a symmetric matrix A, then you can decompose it into its eigenvalues, right? So you have a matrix of eigenvalues. This diagonal matrix here on the right-hand side is a matrix whose diagonal elements are the eigenvalues, right? Matrix D would be the corresponding modal matrix with columns whose columns are the eigenvalues of A. Okay. It's particularly helpful for matrices that you need to solve, and it's going to be tedious to solve if you don't use eigendecomposition. Let me just share the PowerPoint screen again. If you recall this problem earlier, no? If you recall this problem, or actually this is in the problem set. Of course, I'm not gonna show the solution as to why. Pero um there's a problem there that tells you that you can actually get a squared. So you suppose you have a real symmetric matrix A squared, you can actually get uh, the product, right? You can actually get the product of that symmetric matrix, right? Through its eigenvalues, right? So D squared here refers to the matrix of eigenvalues, right? So if I lay this out, in matrix form, right? This is gonna look like this. So sabihin natin, let's suppose this is a 2 by 2 uh, example. Right? Suppose gawin natin siyang 2 by 2. So you have P11, you have P1, 2, you have P2, 1, you have P2, 2. So based on our definition, this is the modal matrix. And the columns here will represent the eigenvectors corresponding to what? Corresponding to the eigenvalues that are located in this matrix. So this is lambda 1, this is 0, this is 0, this is lambda 2, right? And the other one would be the inverse of this modal, what we call the modal matrix. Okay, and you just get the, sorry, you just get the, inverse of this one. Okay. Now you may tell me, that's just a 2 by 2 matrix. So that has to be very simple, right? So if I'm just going to get the square of asymmetric matrix A, I can just multiply it, right? Yeah, for lower order, for lower powers, right? For lower order matrices, that's pretty straightforward. But what if I ask you to get, say, a P? What if I ask you to get this matrix, right? And this is applicable, as we will see in our example, this is applicable in difference equations, wherein the matrix involved, right, is too tedious to solve, right? So how would you even, how can you even start solving, say, this matrix? So from A, sabihin natin, from A1 to A, right? A1, right? So A times A T. How would you even solve that? Right? So it's going to be difficult. So one shorthand is to decompose matrix A. You can decompose matrix A and decompose them into its eigenvectors, in its into its eigenvectors and eigenvalues, and try to solve for A squared using this property. Right? But first, let's first try to solve for the eigen decompose. Let's try to do a spectral or an eigen decomposition first. No? So suppose you have a symmetric matrix A. So let me write it here. You have a 2 by 2 matrix. So you have 6, 2, 2, 3. And I'm starting off with a 2 by 2 matrix kasi this is especially useful. Well, linear system of linear equations or norm indifference for macroeconomics or for difference equations. Normally, you'll just deal with you'll just deal with with two equations and two unknowns, right? A system with three equations is a little bit more complicated. So let's show that A can be represented by d lambda d inverse, right? Where lambda, big lambda here, where lambda is the diagonal matrix of eigen values. So our next task, of course, to show this, we'll just have to solve for the eigenvalues of A. So what are the eigenvalues of A? So let's get the determinant of A minus alpha or lambda I, right? It's up to you, right? You can use any notation. You can use alpha or you can use lambda. But for time series econometrics, they typically use lambda. Or for macroeconomics, they typically use lambda to represent eigenvalues, right? So that's going to be the determinant of what? The 2 by 2 matrix. So 6 minus lambda 6 minus lambda, right? 2, 2, 3 minus lambda. And notice that this is asymmetric matrix. Okay, this is asymmetric matrix. So that's one qualifier. No, you can use eigendecomposition if you have asymmetric matrix. Okay. So multiply this, you will get this determinant. So you'll have 6 minus lambda. You have 3 minus lambda minus 4 equals 0. Right? And solving this, oops. Oh, okay, what happened? Okay, just remove this. Oops. Okay. Uh, sige. Minus 4 equals 0. Okay. So, solving this product, you'll get 18. 18 minus 9, right? 18 minus 9 plus 9 lambda plus lambda squared minus 4 equals 0. Okay. Now, subtracting this, you'll get lambda squared. You get lambda squared minus 9 lambda plus 14 equals 0. Now, when you try to factor out a quadratic equation, always look at the last term, the constant, and try to figure out the factors, no? So, for 14, you can either get 14 and 1 as its factor. So, 14 times 1 equals 14, or you can get 7 times 2 and their negative equivalent. So, the most sensible factor that we have here would be negative 7 and negative 2. So negative 7 times negative 2 is positive 14. Now, if you add negative 7 and negative 2 together, you'll get negative 9. So obviously, the factor of this quadratic equation would be, the factors of this quadratic equation, or the zeros of this quadratic equation would be lambda minus 7 and lambda minus 2. So try to multiply this and you will get lambda squared minus 9 lambda plus 14. Right? And therefore, the eigenvalues, right, so the eigenvalues would be, for lambda 1 will be 7, right? And lambda 2 will be 2. Okay. Now I can construct this middle matrix. I can now construct this diagonal matrix, no? So the diagonal matrix lambda, big lambda, will be this 2 by 2 matrix. So you have 7, you have 2, you have 0, 0. Okay. Now it's just a matter of solving for D and D inverse. Okay. So let's solve for D and D inverse. Okay. So let's solve for the eigenvector of, say, let's start off with 7. Okay. Or maybe you can just switch this now. Okay. Just to be consistent with the slides earlier. So this is 2, this is 7. That's fine. No? Let's solve for the eigenvector of lambda 1, which is 2. Okay, let's have new slide. I suppose we'll get lambda equals 2. Okay. So if I substitute 2 here, no, I'll get a minus lambda I, right? This becomes what? 6 minus 2. This becomes 6 minus 2, 3, 2, sorry, 2, 2, and 3 minus 2. And this becomes 4 4, 2, 2, 1. Okay. Now, solving this, no, and actually have a vector of x's here. And now, since we know that the eigenvector is non-zero, oops, the eigenvector is non-zero. So x1, x2, and the eigenvector is non-zero. So you have 4x1 plus 2x1, that's equal to 0, right? You have 2x1 plus x2 equals 0. Okay. So if we let x2, so remember that when we solve for eigenvectors, you'll have to make some assumptions, no? So suppose we let x2 equals 2, right? If x2 is equal to 2, right? If x2 is equal to 2, x1, right? So I move 2x1 on the right hand side, right? So you'll have 2x1 equals negative 2, right? Or sorry, if I move x2 on the right hand side, I'll get 2x1 equals negative 2, and therefore x1 will be negative 1. Okay. By the way, you can just start with the second equation kasi the first equation here is just a multiple of 2. You multiply this second equation by 2, you'll get 4x1 plus 2x2. So practically the same, right? So substituting 2, right? The eigenvector, let's denote that as x1, the eigenvector x1, and that's going to be negative 1, negative 1, and 2. Okay. Now for alpha 2, which is equal to 7, or sorry, for lambda 2, which is equal to 7, right? So a minus lambda I will be equal to this matrix. So that's going to be 6 minus 7, negative 1, negative 1. This is going to be 2, this is going to be 2, and this is negative 4. Okay. And you have another vector here. You have your eigenvector here, right? x1, x2. And this is supposed to be equal to 0. Okay. Now, multiplying this, so you'll have negative x1 plus x2, or sorry, for plus 2x2 equals 0. Okay. So you can just stick with the first equation, but if you want to write it out, that's fine. So 2x1, you have 2x1 minus 4x2 equals 0. So again, in eigenvectors, you need to make some assumptions. So let x1 be equal to 2. So then x2, right? So if I let x1 equal to 2, then 2x2 moving x1 on the right hand side would be equal to what? Positive 2, no? And therefore x2 would be equal to 1. Right? Therefore, our second eigenvector x2 would be equal to what? 2 and 1. Right? So we're going to use, so let me just write everything down. No? Our big lambda earlier, or the diagonal matrix of our eigenvectors, would be equal to uh, 2, 0, 0, 7, right? As noted here, our x1, or our first eigenvector, right? x1, oops, x1 is equal to this vector, so -1 and 2. -1, 2. And then you have your second eigenvector is equal to 2, 1. Right? Now I can construct matrix D. So what's matrix D? Matrix D is basically equal to what? X11 from here, right? It's just basically equal to x1, the vector x1 and x2. Or you basically combining these two vectors together. So you have -1, 2, 2, 1. All right. Now, now it's just a matter of multiplying or showing that A is indeed equal to D lambda E inverse. Right? Because we already have the components. No? We already have the components. We already have matrix D. We already have lambda. Only need to find out is the inverse, no? Inverse of D. So to get the inverse of D, so that's going to be D, right? So we'll need to get the cofactor. We need to get the determinant muna. No? So the determinant of D, determinant of D is equal to -1 minus 4. So you have -5. Okay. So the cofactor matrices would be, the cofactor of D would be another matrix obtained by deleting the corresponding rows and columns and getting the determinant of those columns. No? So that's going to be 1, 1, right? Delete the first row, second column, you have -2. Then you have, you delete the second row, first column, you have another -2. And then you have, um, uh, you have 1. You delete the second row, second column, you have -1. Okay. And then getting the transpose of this matrix will yield the adjoint of D. Adjoint of D will just be the transpose of this 2 by 2 matrix. So you'll have, and since this is symmetric, this is equal to the adjoint of D. Right? So you get the transpose, a symmetric matrix. If a matrix is symmetric, if you get the transpose of that matrix, you'll get the same. You still get the same matrix. So if I transpose this, I'll still get 1, -2, -2, -1. So now the inverse, right, the inverse of this matrix is equal to 1 over. So again, you have a 2 by 2 matrix here. So you have -1/5. You have -1 over 5. You have 2 over 5. You have 2 over 5, and you have another 1 over 5. Okay. Now we'll just have to multiply these matrices together. Okay. So A is equal to, we said that A is equal to D lambda, D lambda D inverse. Right? So what is D? Matrix D is the modal matrix or the matrix of the eigenvectors. Right? So that's going to be 1, uh, negative 1 rather. You have negative 1, 2, 2, 1. You have your diagonal matrix of eigenvalues. So you have 2, 0, 0, 7. And then you have the inverse matrix. What's the inverse matrix? The inverse matrix here would be uh, negative 1/5. You have 2/5. You have 2/5, and then you have 1/5. Now, you can either, by associative property, you can either start with this matrix first, yung lambda and D inverse, or you can start off with D and lambda. Doesn't really matter. Right? You'll still get the same result. So let's start off with the first two matrices. Right? So this is going to be equal to negative 2. You have 14, you have 4, and 7. Okay. And then you still have the 2 by 2 matrix here. And just to verify, no, so you have negative 1 times 2, negative 2, plus 2 times 0, negative 2. So you have negative 1 times 0, 0, 2 times 7, 14. You have 2 times 2, 4, plus 1 times 0, which is 0. So you still get 4. And then you have 2 times 0, 0, plus 1 times 7, and that yields 7. And here you have negative 1/5, you have 2/5, you have 2/5, and then you have 1/5, right? And this is equal to another 2 by 2 matrix, right? So 2/5, so you have positive 2/5 plus 28 over 5. Right? So basically, that's 28 over 5 plus 2 over 5. And that yields 30 over 5. Right? And 30 over 5 is equal to what? It's equal to 6. Right? So that's the first element. The second element, you multiply negative 2 by 2 over 5. So you'll get negative 4/5 plus what? 14 times 1 over 5. That's 14 over 5. So essentially, you have 14 over 5 minus 4 over 5. And that yields 10 over 5. And 10 over 5 is equal to 2. Okay. Next, you have the second row, first column. So you have 4 times negative 1 over 5. So that's negative 4 over 5 plus 14 over 5. So that's another 14 over 5 minus 4 over 5. That's 10 over 5. And then you'll get another 2. Right? And lastly, you have 4 times 2 over 5. That's 8 over 5. Right? And then you have 7 times 1 over 5 times 1 over 5. And that's 7 over 5. So you have 8 over 5 plus 7 over 5. That's 15 over 5. And that simplifies to 3. And that proves that A can be decomposed. The symmetric matrix A, which is 6, 2, 2, 3, can be decomposed into its eigenvalues and eigenvector components. So this will be your modal matrix of eigenvectors. This is your matrix of eigenvalues, and this is your matrix of um, the inverse of the modal matrix. Okay. So any questions at this point? Actually, I'm thinking of just leaving the application to you. You can just verify the exercise. But basically, I'm not even sure if you can if you encounter this later on in your macro economics. But just for additional reference, the reason why we are doing this eigen decomposition is that for higher ordered matrix or higher powers for the matrices, uh, it might be more straightforward. Right? It might be more straightforward to do matrix decomposite or eigen decomposition if you're asked to get, say, the product of higher ordered matrices. All right. So any questions?
Sir, for lambda, if we interchange the position of 2 and 7, are we supposed to get the same answer uh, for the proof?
Ideally, yeah.
Okay, thank
Yeah.
you.
Ideally, yes. That's the nice thing about eigenvalues. Even if you switch the eigenvalues along the diagonal, you're supposed to get uh, the same. You can verify that. You can verify that. Any other questions?
Answer.
Okay. All right. So if you have any other additional concerns, yeah, you can just post it in our discussion, topic Q&A in Canvas, no. And next meeting we'll start off with our new topic, which is basically functions and limits. Um, for those who are still new to algebra or really need to refresh their knowledge of college algebra, and next chapter will be such a review. No, so we will talk about functions. No? Very briefly, we're going to talk about functions. And okay, let me just stop the recording now. No,